Hello, this presentation is for solving the problem of motion planning for multiple autonomous vehicles using an algorithm called Rapidly Exploring Random Trees or RRT. The introductory part of the presentation is in a different video, the link to which should be in the video description. So before we go on solving this problem using the concept of RRT, let's see what RRT basically offers. As a trajectory planning algorithm, the good thing is that RRT is probabilistically complete. So if a solution exists, it will be able to eventually find it out. In fact, for most of the situation, unless there's a very critical narrow path involved, where a part or a good part of the trajectory goes through a narrow path like this, where all sampling based approaches really struggle in order to get this robot inside this robot, because the probability of a random sample being generated inside is too low. In all other cases, RRT is probabilistically complete and it is reasonably fast. It's much faster than GA, and naturally it has some disadvantage, which means that it is not optimal. Now we'll specially see into when is it not optimal. Now if there is an obstacle like this, there is a source, there is a goal, the RRT cannot find out whether this is a better path or this is a better path. Clearly it looks that this one is the better path, but RRT may eventually succeed in generation of this path. They are not very optimal. If this much of a difference does not make much of a difference to you, then it does not matter. You can use RRT as an algorithm. In fact, mostly what will happen if I place another obstacle like this, RRT will mostly never generate this path, which is clearly very bad. The other problem that from an optimality perspective that RRT faces, suppose the source was here, the goal was here, there is an obstacle out over here. Now clearly this is the optimal path and this path is very long, but this path goes through something which is nearly a narrow corridor problem. I should have ended up this like this. There is enough space, it isn't really a narrow corridor problem, but because it is somewhat difficult to enter into this path, RRT may actually make the algorithm enter into this path. And they are locally optimal, which means this path or a slightly longer path or slightly tilted path, RT can generate anything. So the problem is that they are suboptimal in general. If this much of suboptimality is okay, then it should be okay to use such kinds of problem, but if clear optimality is needed, then these are not the algorithms of choice. So we'll take a quick in-depth into what RRT are, how do they function. First, from the point of view of mobile robotics, if this is the source and this is the goal, I need to find the trajectory that connects the source on the goal when given there are some obstacles around like this. Now from primitives I know that graph search is a very good technique to find such kinds of trajectories. In fact, graph search are since long been known the algorithms of choice to solve on all such kinds of problem. If I can have a graph somewhere around magically appearing here, then I can solve the problem as a standard graph search procedure or a standard shortest path graph search problem. The problem is that I do not have this graph here. If I take each and every pixel and the correspondingly a rich set of actions, it will become computationally very expensive. I don't have that much amount of time. So I need to do something so that a graph appears out here. So let's start drawing random edges of this graph. And because I'm drawing no back edges, then it will ultimately not be a graph, it will be a tree. So what I'm doing, I'm basically drawing in random edges as and when I feel like. I just insert in an edge in the forward direction, and this gets in the form of a nice tree which is known as RRT. It stops as soon as I reach the goal. So let's say here I have reached the goal, then it stops. The complete tree extension procedure will stop as soon as I reach the tree, and this little nice graph that you see out here, or because it has only forward edges out here, this is what is known as an RRT. And after I found out such an RRT, my search problem is very simple. There's only one path in this graph or in this tree that connects the source to the goal, which is this path out here. This will be returned as my trajectory, and it doesn't look that bad either. So the thing is that I'll randomly generate in some graph out here or some tree out here by drawing in random edges in the forward direction. And the way I draw random edges in the forward direction is very simple. Let's say this is the source and this is the goal. There's some amount of expansion which had already taken place. This was the tree which was already available at some instance of time. The way that I extend this graph is very simple. Step 1, I generate in a random point here. Anywhere inside this map, I generate in a random point in here. I find out the closest point in the RRT available, and I simply extend this point towards this X by a step size, say S. And if this edge is obstacle free, if this complete edge is obstacle free, then I add it to the RRT. Similarly, next time step, let's say this is the random point generated. This would be the extension. Let's say there was an obstacle here. The next time, this is the edge. The random sample generated. The closest point is this. Now I cannot add this edge. This is inside obstacle, so it won't be added. If this is the next edge here, this will get extended by S. So this is how RRTs grow. They expand, and that's why they are called as RRTs. They are trees. That's where the T comes from. They are random, because I'm generating random samples inside, and they grow very rapidly. It doesn't take time to generate and grow this type of tree, so they grow very fast. They explode very fast. That's why they are called rapidly exploding random trees. Now coming to the problem statement, was for motion planning for multiple autonomous vehicles. So what I'll be doing, I'll first be solving the problem for a single autonomous vehicles. I'll not be considering any vehicle other than the vehicle being planned, and then I'll extend the framework so formulated to the presence of multiple vehicles. I'll generalize the algorithm for multiple vehicles using what we know as coordination, the problem of coordination. So firstly, let us consider the single problem of planning of a single autonomous vehicle. I have been given some kind of road like this, which has some obstacle. Say here, there is a vehicle which is the source. The second thing I need to do is the goal. I said goal is any point out here. Unlike some other approaches, RRT does not need a very clear definition of a goal, so I can say that goal is any of the point out over here, or there are multiple goals, any one of them can be reached. Now vehicles cannot make a very sharp turn. If the vehicle is in this direction, it cannot go like this, it cannot go like this, it cannot trace these trajectories, it cannot suddenly turn. So my RRT generation, the first child must always be in the current heading angle of the vehicle. So my first child is always fixed. So if this is the source, I'll only consider the current heading angle and produce the first child, after which I can do anything. Once I generate in this child, I'm rest assured that my trajectory would be like this, my trajectory would be like this, anything like that, which can be traced as per the current heading angle, as per the kinematic or the non-holonomic constraints. So my first child is fixed for this particular problem. The second thing, of course, as we know, is that I'll have to generate samples which are feasible, and for that I'll have to use the road coordinate axis system, where this is the x-axis, and at any general point the perpendicular one becomes the y-axis. Let's say this is x and y dash. So these are the two primitives that I would be using, and using which it becomes very clear that I can solve the problem. So this is a nice picture that I have drawn. This was the vehicle source. This was the current heading angle. This becomes the effective source, after which I completely randomly generate in points. I randomly grow in my RRT like this, and ultimately like this kind of exploration in and around it will ultimately reach the goal, and this will become the trajectory to be traced. So I can solve this problem. My first problem, part of the problem, is almost solved in this mechanism. The if In RRT we always have one very important concept which is called as biasness. Suppose in first, let's talk in the terms of mobile robotics. If this is the source, if this is the goal, and there's some obstacle framework out here, I do not want my RRT expansion to basically cover this entire map to generate all kinds of nodes. It will take a lot of time, even though they are rapid. It will take in a lot of time if I explore this complete map. Effectively, what I want is that it should go as soon as possible towards the goal, or what is known as the search should be biased towards the goal. The exploration should be towards the goal. The exploration should happen such that goal is reached as fast as possible. So that is what I need to do. I need to bias my I need to bias my exploration towards the goal, and that is what we do. That I said, I told how the general expansion works. It firstly selected random point. Some bit of time we select goal as a random point. So whatever are the point nearby, they get expanded towards the goal. So again, I taken a random scenario where this might be the RRT, and there might be an obstacle here. I'll take goal as the sample. I'll extend the nearest node, which is this, towards itself. This will become the extended node. Then I'll take in a random sample again, Then again I'll take in goal as a sample. So many times I take in goal as a random sample and extend the nearest node towards the goal. So what will happen is that the exploration will happen as it was happening. The entire search space will potentially get explored, but the entire exploration will happen more towards the goal. Now, was in terms of mobile robotics. Now what I need to do is that I need to implant this idea into the autonomous vehicle scenario. And one thing is very simple, that I can do it straight away. I can select most of the time any general point out here as the goal. But we can do much better than that. We can carry out biasness much better than that. If this was the vehicle, this was the source, this was the effective source after the heading angle. Now we know the vehicle will most probably not like to come into these areas because it will ultimately require such large steering. It will prefer to stay mostly in this region. If there's some obstacle here, it might go here, it might go here, but it will completely be unpreferable to go in regions very far off. So in a road scenario like this, I'll draw this again. In a road scenario like this, what we'd say is that this is the most favorable region. This is slightly favorable. These are the slightly favorable regions. These are very unfavorable regions. So as we go away from the current heading or lateral position of the vehicle, sorry, not the heading, as we go away from the lateral position of the vehicle, the probability of sample being generated there reduces. So I'll generate more sample in this region and very less sample in this region, and that's why my RRT will be mostly around this region, and only if an obstacle is found such that a high amount of steering is mandatory required will these areas be explored. So what I've done, I biased my RRT expansion towards this narrow region. Now it plays a very good role in computational boost up. Now only effectively this part of the road is to be explored given there is no obstacle. The other very unfortunate problem with the use of RRT is that they generate in very funny paths. So in a very simple road like scenario, they'll generate paths like this. And the spikes, of course, they cannot be traversed. The spikes denote in regions of a very, in fact, if it's an actual spike, no matter how careful, how strong you steer it, you'll never be able to follow it. Vehicles can only take smooth steering, or they can only traverse smooth paths. So an element of smoothness has to be introduced. An element of smoothness so that the actual trajectory is traversed by the vehicle. One way of saying it would be very simple, that let this be the path to be tracked by the vehicle. The controller will automatically, the controller can only generate smooth paths, so the closest trajectory it will generate. But if this trajectory was obstacle free, it cannot be ascertained that the smoothed version of it which the controller actually tracks will be obstacle free. Maybe what the controller does is to trace in this trajectory where here the vehicle might collide. So I need to be assured that the trajectory is smooth as well as obstacle free, and that will be the next challenge. And this is what we call it as the smoothened RRT, or the RRT with all smoothed edges. What I've done is very simple. It's the same old RRT that we saw in the previous slide. It is exactly the same RRT. What we've done is that after every node, I use all these points or the paths from the source. I find out the path and I simply pass them through these spline curves, which generates in a smooth curve like this, and that is what I've overlaid. I've overlaid the smooth spline curves over the old RRT. So for the expansion, for the working with, for extending, I'll be using the actual RRT which lies underneath. I'll be using the same discrete non-smooth RRT, but along with it, after every insertion, I'll use the spline curves to generate in a smooth trajectory that smoothens the tree so formulated, and that's what has been shown by this yellow curve. Now here we've additionally shown this is the relation of velocity to the curvature. Once I know I have the smooth RRT, I can find out what is the maximum speed by which the curve can be traversed. I can basically find out if there is a curve, what is the maximum speed by which this curve can be traversed. If the maximum speed by which this can be traversed is greater or equal to the maximum speed to the operating speed of the vehicle, then I say that the curve is correct. It can be traversed by the controller. The controller will have no problem. I accept it. If the speed happens to be lower, that means a very sharp curve exists out in the RRT. As for example, let's say that I generate in a new curve like this, and the extension happens like this, and the smoothened RRT is like this. Now this is a very sharp turn. The velocity will come out to be much lower than the operating speed of the vehicle, and I'll not admit this solution. I'll say that this node cannot be added. So this is an additional check that I have produced of curve smoothness and velocity check, that every addition should produce a smooth curve which is traceable by the vehicle. And that will be all for the first part of the problem, where I was not dealing with multiple vehicles. I was dealing with a single vehicle. Now I have a very simple strategy to extend this solution of a single vehicle to multiple vehicles. Let us say that I have a road, say like this. There are a number of vehicles like this. Earlier I was only considering one vehicle, now I'm considering multiple vehicles. I use priority based coordination, which means that the vehicles will be prioritized one by one, and a vehicle higher to on the road is has higher priority than a vehicle ahead has higher priority as compared to the vehicle behind. So let's say this is priority 1, this is priority 2, this is priority 3, and this is priority 4. Priority 1 vehicle considers no other vehicle. It simply formulates its trajectory, and that's simple because clearly it will not collide with any of the vehicles behind. Priority 2 vehicle also considers no other vehicle except for priority 1, and clearly in this case they will not collide. Priority 3 vehicle is here. It has to formulate its trajectory such that it does not collide with number 1 and number 2. The trajectory of both of them are known. So I first planned the trajectory of this vehicle, I then planned the trajectory of this vehicle. Once I come to the vehicle number 3, The trajectory of this is known, the trajectory of this is known, so I can treat both of them as dynamic obstacles and formulate a trajectory for this vehicle such that no collision is possible. And then comes trajectory 4. Vehicle 4, once I'm planning this vehicle, the trajectory of all these three vehicles are known, and I can simply treat them as mobile moving obstacles, obstacles whose motion primitives are known. And once I do that, I can very simply treat them as obstacles as in a general framework of the RRT and compute the trajectories. In implementation, what we have done is that the vehicle 1 enters the scenario. It computes the trajectory. It sees no other vehicle. It continues its trajectory somewhere. If it's here, then the vehicle 2 will enter. It will be out here. It will find a trajectory such that it does not collide, while this vehicle continues to go as per its all the planned trajectory. The vehicle 1 does not pre-plan. Vehicle 2 computes this trajectory. It continues somewhere. When it's here, vehicle 3 enters. Now vehicle 1 and 2 are not re-planned. They retain their original plan. Vehicle 3 is planned so that it does not collide with any Ds. So that's how practically that is done. So that is the first very important aspect of coordination. It's a priority based coordination with vehicles higher up having higher priority than the vehicles back. Only the lower priority vehicles consider the higher priority vehicles in the trajectory plan, and they can very simply consider, because once the dynamics of the vehicles of the higher priority vehicles are known, they can be treated as simple obstacles as inserted in the general problem solving methodology of the RRT. Now what is important, because it is a multi-robot planning problem, or let's say it's a multi-vehicle planning problem. In the case of multiple vehicles, what happens is that the speed of operation is of importance. In case of single planning vehicle planning problem, if I find out this trajectory, it can be traced at any speed. It does not matter, because all these obstacles are static. I can travel at 10 miles per hour, 20 miles per hour, 30 miles per hour. These obstacles are static. It does not matter. The trajectory would still be good. In multi-robotics problem, these obstacles become static, and hence if I travel at 10 miles per hour, maybe it is collision free. But if I plan at 20 miles per hour, maybe this obstacle was moving here, or this vehicle was moving straight away. At 20 miles per hour, maybe I dash out over here. A better way to look at the same thing would be, suppose the road is like this. There's a vehicle at the back, there's a vehicle in front. This is traveling at a very low speed, and this is traveling at a very high speed, and there is no possibility of overtake. The road is small. Now this vehicle has to reduce its speed. It cannot overtake. If it does not reduce its speed, it will not be able to find out a path. So I have got an additional problem. I do not have to only plan for the path, I also have to plan for the speed in my RRT. And the RRT, we know they only plan for the path, so I'll have to do something to fix the speed of all the vehicles. And I've taken a very simple fundamental. Say I'm planning for the vehicle 4 out here, the maximum speed of which is v. So I say I ask the RRT, can you generate a feasible path at speed v? If yes, well and good. Else I'll say that, okay, since you cannot generate a feasible path at speed v, reduce the speed. Can you generate a feasible path at speed v minus delta? If you can generate, well and good. If you cannot generate, then can you generate a feasible path at v minus 2 delta? So I'm constantly reducing the speed and asking RRT, can you generate a feasible path? Can you generate a feasible path? Eventually some speed will come, v1, when RRT will say that yes, this is the feasible path. And if this delta is small enough, then I can say that v1 is the highest possible speed as per the current scenario and as per the current prioritization that the vehicle 4 can navigate. V1 will be the highest speed that the vehicle 4 can navigate. Of course, if delta is too small, then I'll have to call RRT too many times. It will take time before I reach speed V1. And if it's too large, then V1 will be way further off from the actual highest possible speed to generate in a feasible plan. So that's way in which I fix speed. I basically start from very high speed. I keep on reducing the speed till I find till RT is able to generate in a feasible plan. Now there are two. Uh, with respect to the other works that I'm presenting as videos, there are two important points to note. Firstly, this coordination is non-cooperative. That means if a vehicle behind is trying to overtake a vehicle in front, this vehicle will not go towards the side. In order to make the overtake simpler for this vehicle, the vehicle will actually have to go by a very odd trajectory. Coordination is non-cooperative. And they could have, there are variations possible by which we embed in some simple kind of heuristics in order to make the travel plan cooperative, where this vehicle is asked to weave towards one side to make the travel plan cooperative. But in the current version, we haven't really done that. The second point to note is that suppose this vehicle is following this vehicle, there's no way that overtake was possible, and somewhere later on overtake becomes feasible. Now I'm planning with a uni-speed model. The speed variations cannot, in my current plan, the speed variations are not admitted. That first half of the plan will be at some speed V1, the second half of the plan will be at speed V max or speed V. This I'm not doing. So if a vehicle follows in the other vehicle, it will continue to follow until, of course, the end of road segment is reached and the plans of both these replanning is done for both these vehicles, when overtake might be feasible as per the plan generated later on. But once the vehicle decides to follow, it will continue following, which is another limitation of the work. And these are the results using RRT. You can simply see that the obstacle frameworks were quite complex and the vehicle could easily overcome. I've told a lot about I've plotted many hypothetical tree. This is the actual tree that was generated, a very complex framework, and you can see that we biased towards this region, and that's what's explored, and this is the smoothened version of the tree. For multiple vehicle, they are planned in a prioritized manner. This is the normal vehicle following behavior, where the green vehicle follows the red, and this is the overtake behavior. The green vehicle overtakes the red vehicle. Here the two vehicles are generated from opposite side, one from here, and they clearly avoid each other using quite good separation. There's a single parameter involved, which is step size, which basically means by what magnitude do I extend my tree. If I extend it by too much, it means I'm aggressively moving towards the goal. By very, very large steps, I'm aggressively marching forward, which of course means that my entire tree will have lesser number of nodes. But on the contrary, if I'm very aggressively following towards the goal with very large step size, most of the time I'll end up either dashing up in the road boundary, where the entire extension has to be nullified, or going inside some obstacle. So the effort required will be very large. If the step size is too small, I'll be walking towards the goal in extremely small steps, and therefore the time required will be very large, and therefore the minima lies somewhere in between. Now that was one thing that we done, which was in fact presented in conference. The work was extended. So here what I'll be doing is that the complete process I'll be repeating, where we first plan for a single vehicle, then we extend the planning for a single vehicle for multiple vehicles. And apart from that, the algorithm is slightly different from RRT. It's called as RRT-Connect. What here the approach would be that I'll state what were the limitations of that work which we presented at the conference, and how did we overcome them in the next paper that we worked upon, which was using RRT-Connect. So of course, first I'll be stating what are the difference between RRT and RRT-Connect. And RRT, if this is the source, this is the goal, there's some obstacle out here, I expand in tree like this. In RRT-Connect, what I do is that after every expansion, say this was the expansion, I'll see if I can reach the goal by traveling in the same direction. So I keep on extending up till I reach something. Now it may look funny, why do I RRT-Connect is very good in rapidly solving the problem for a very simple scenario. So if there are no obstacles, I'll very quickly be able to come straight to the goal. In the road version or in the vehicle version, what we do is that if this is the vehicle, this was the source, I always had to add the first point, which is the source. But then since I am adding in a point, I'll see if maintaining the same lateral position, can I reach the goal. And of course, as it's clear from here, if there are no obstacle, if there are no other vehicles, then of course I can reach the goal. So basically the algorithm did nothing. It simply used the current heading of the vehicle and it tried to see if reaching the goal from this position, maintaining the current lateral position is possible. It is possible. There are no other vehicles around. There are no obstacles. Even if there would have been a vehicle ahead traveling at a greater speed or equal speed with this vehicle following this vehicle, the same thing would have happened. I would have generated S dash and asked whether this trajectory is feasible. Now note that this trajectory is feasible because when this vehicle comes here, this vehicle comes here. When this vehicle comes here, this vehicle comes here. So there's no collision possible. When this vehicle comes here, this vehicle is out of the road segment. So that's a very beneficial boon that there is a very significant boon that we get by using RRT-Connect as the algorithm, because any type of traffic scenario that you see, mostly vehicles are following each other. So there should not be an intensive computational setup to generate in the most basic behavior. And that's what RRT-Connect will do. There will be almost no effort in generating a vehicle following behavior or driving in behavior where there are no vehicles ahead. Now, an unfortunate problem with the conference paper or the RRT that I just presented was that every time we had to go from the source to the current expansion. So let's say if expansion is having like this and I expand this node, so right from the source I had to produce a spline curve here like this in order to test the feasibility, in order to compute the costs. Now I must mention this is not really a limitation of the RRT using spline curves. If I have the smoothened version of the RRT, I can directly use the smoothened version to extend one arc here. In place of extending one line, I can directly extend one arc without having to see right from the source how this arc would be produced. The unfortunate problem was that I was using in a custom MATLAB library for producing spline, because of which only this extension was not possible. We had to give the control points right from the start. Now, even though triggered by this, so in this new work what we do is that we do not use smoothness at this stage. We'll be working on the basic unsmoothened RRT, and we know that a unit extension of the RRT, just extending one node to produce an arc like this, it costs nothing. It takes in very less time. It was the generation of a curve which was taking time, so we've saved in a lot of time by getting rid of this curve generation. And as I mentioned that for the most basic behavior, I take in a unit time step. So by these two slides, it is clear that I need to explain nothing more in the use of RRT-Connect for solving the problem. The same RRT-Connect methodology would be used, and like RRT could solve in scenarios like this by some kind of expansion from the source to the goal out here. RRT-Connect will be able to do that in a very similar manner. There are two problems associated here, which were the limitations of the first work of the RRT. The first problem that I stated, that RRTs are not globally optimal. So if this is the optimal path and this is not the optimal path, maybe RRT-Connect or the RRT for that sake, it returns me this path, and when I could simply drive in straight, I unnecessarily have to steer in. It is possible. Say this region was narrower than this region, it is very well possible. So this is the first problem that I have to solve. The solution to this is that I call the entire RRT procedure a number of times. So let's say I call the RRT procedure 5 times. This does mean that my RRT-Connect algorithm now will take 5 times the computation cost that the RRT-Connect algorithm I presented so far would be, that the previous RRT-Connect that I presented would be taking. It will take 5 times more cost, but where does this time come from? I've saved in a lot of time here. Because I've saved in a lot of time here by not considering smoothness, I can invest in that saved time. So in how do I invest in trying to get the global optimality, and how do I get the global optimality? Calling this 5 times and selecting the best. So maybe 3 times it goes in from here, 2 times it goes in from here. I compare the cost of all the 5 times, I clearly see this one is better, and I select this one. So I'll be calling RRT a number of times and the best solution will be generated. But this only solves in a part of the problem. The other problem is that RRT are not locally stable as well. So let me instead say my scenario was like this: my vehicle here, my obstacle here, a small obstacle here. The RRT cannot decide between this path, this path, this path. And by the way, because it is RRT, they generate in very funny solutions. It will generate in these kinds of solutions. Now in general, what in the previous work I did not do, it was a conference paper. What we always have to do, we have to get rid of these things. Because a spline version of this would be like this. No, even this is not good. We don't want to sit in a car which keeps oscillating unless we are going in for a fun drive. We don't want to sit in a car like this. We want to sit in a car which goes like this. If you need to transform this path into this path, you will have to do what is known as post-processing in some literature, or what's known as local optimization. This solves in 2 purposes. Firstly, it will delete all the excess points out here. So when I delete all the excess points out here, I get a smooth curve where only the necessary points are there in the entire path. The second thing it will do is, that it will select whether this path is good, whether this path is good, or whether this path is good. It will based on the cost function that I provide, it will select which one of these paths is good. And how it will do is that, suppose there are 4 points that this trajectory represents. There are 4 points which are joined by a spline curve which produce the trajectory. It will try to move each of these points a little left, a little right, a little up, a little down, and it will see what is the best setting for all these points, and correspondingly it will be able to select the best out of all these trajectories. So my resultant approach is near globally optimal. I can still not be sure. Maybe this curve was really small so that all 5 times this path gets generated. It will be near globally optimal, and it will be near locally optimal. And for this part, of course, I use the spline curves. All the points that the RRT represents were passed to a spline curve to produce the smooth curves, which was worked over by the local optimization strategy. So I have solved both these problems. And again, for the local optimization, where does the time come from? The time comes because I have saved in some time here, which I'm not only using for global optimality, I'm also using the same time to get near local optimality, and that is how the incomplete problem is solved. Now, I have planned for a single vehicle. The only thing that I need to do is coordination, where I plan for multiple vehicles. The approach would of course be very similar to what I just presented, that prioritize all the vehicles. A higher priority vehicle, the low priority vehicles considers only the higher priority vehicles. A lower priority vehicles is responsible for all the collisions, and because the trajectories of the higher priorities vehicles have already been computed, they can be treated as static obstacles which the low priority vehicle can avoid. The second thing that I said there was that speed is iteratively reduced from v to v minus delta to v minus 2 delta. Now this is a very bad procedure to v1. I'm calling the complete RRT so many times in order to get the best, highest possible navigable speed here. I cannot waste this much amount of time by calling the entire hefty RRT algorithm so many times. So here in RRT-Connect, what I say is that I call the RRT with connect by a speed v, and I see what happens. If it says the path construction is infeasible, I do not let RRT get rid of it. I further ask it, why is it that you could not construct a path? What was the reason by which feasibility is being not catered to? And if it says that it is not, that I'm unable, if the RRT Connect says I'm unable to construct a feasible trajectory because of collision with another vehicle, because if there's another vehicle with which I'm again and again colliding, I cannot surpass that, then I'll ask in which direction was that vehicle moving. Suppose the RRT could not overcome this vehicle. It tried to expand the lot, but it cannot overcome this vehicle out here. It tried generating many samples all around here, it still could not overcome this vehicle. Then I say, very simple, if this is traveling at speed v2, now I call the RT algorithm one with speed v, the second time I'll call with speed v2. And of course, when these two are traveling with same speed, this vehicle will be following this vehicle, these two cannot collide. Similarly would be if it was if it could somehow overcome this, if it could not overcome this thing, then I would have said that first try the maximum of these two vehicles, speeds of these two vehicles, and try the minimum of these two vehicles. In the worst case, it would have been forced to follow both these vehicles. On the other hand, if it could not avoid this vehicle somehow, now the vehicle following heuristic cannot be used. I mean, I cannot say let the speed of this thing be this thing because these two are traveling towards each other. Then I'll have to say you cannot generate from v, then generate by v by delta. If you still cannot generate by v by 2 delta, the approach which I was following previously. In this figure it becomes very difficult to say why this vehicle would ultimately not be able to continue its journey because of collision with this vehicle. So because of that, consider another scenario. Suppose there's a static obstacle out here, there's a high priority vehicle out here, and there's a low priority vehicle out here. With V, it might be colliding with this vehicle because this vehicle has a trajectory like this, it is overcoming the obstacle. With V minus delta, again, it might be colliding with V, it might be colliding somewhere around here. With V minus delta, it might be colliding out with somewhere out here. Surpassing is not possible. With very small speed, ultimately it will be here while this vehicle would have crossed. After that, generation of feasible trajectory would be allowed. So that's what I do. If infeasibility is due to collision, or if infeasibility is due to vehicle at the same speed, I simply follow the vehicle following heuristic, where I equate the speed of this vehicle to be the speed of the vehicle in front. If it's with the other side, I have no other option than to decrease the speed by some small steps, and these are the results with a single vehicle. Again, it's able to generate the nice paths. What should be considered here is that here the algorithm did nothing. First expansion, straight to the goal. Here, after this expansion, it went straight to the goal. And here after it expanded this, the first expansion was in the heading direction, the second expansion was say here, there would have been some expansion here, but after it reached here, it went straight to the goal. And these are with multiple vehicles, the overtaking phenomena where this overtakes the red vehicle and this overtakes the green vehicle, and this is again the overtaking phenomena, the green vehicle overtakes the red, and here it's simply following the green vehicle cannot overtake, it simply follows the red vehicle. And these are the multi-vehicle scenario, this vehicle comes and these two vehicles avoid each other. And some more results, one vehicle is generated from here, the other from here, and they two decide how to avoid each other. The good thing is like this, the first vehicle came here, the second vehicle knew it cannot go in from this direction, so it instead went in from the other direction. And again, this is the actual RRT generated. As pointed out, the generation happened only till here, after which straight to the goal path was possible. This is the smoothen after local optimization technique, the trajectory that is generated, and this is the trajectory that the vehicle traces. With two vehicle again, now that was the RT generated with first vehicle. Now I'll be presenting the RT generated with two vehicles. Now this is the scenario at which the second vehicle here enters. The green vehicle enters, it sees this. This is exactly what it sees. The first expansion is fixed, and then it can be seen. I'll overdraw the expanded lines out over here. It carried out this expansion in any order. It saw a vehicle, it said that it tried to overcome from the left. It simultaneously at some instance tried to overtake from the right. Once this node was generated, it saw that now I can simply travel right towards the goal. This is what the smoothened version of the same trajectory, and it simply travels straight to the goal. The basic RT algorithm, we know that would have continued expansion like this all around in this narrow region until it would have reached the end, so I save in a lot of time. And whenever I use anything like local optimization or any optimization technique, I need to show that how do the iterations, how do the costs decrease along with iteration, or how does the path improve along with iteration. Now one thing to notice is that I had first generated a RRT path like this, and then I use spline curves to locally optimize it to produce something like this. When I directly used spline curves, when I converted this to spline without local optimization, so the zeroth iteration, it came out to be infeasible. So there was some obstacle out here. When I directly converted this to spline, the vehicle happened to collide, and subsequent generation of the local optimization technique pushed this point down until it became a nice little trajectory like this, which in fact happened at the very second iteration. This point moved by a sufficient amount, and the path became first feasible, and then it was further optimized. So that will be all for the presentation. Thank you.